In this video, we're going to introduce binomial random variables. So to start off, suppose that a coin is tossed 3 times. Let's let x be the number of tails in the three tosses. Write a probability distribution for x. And as a hint, use the sample space to find these probabilities. So I'm actually going to let you try this problem out, and we'll talk about it in just a moment. Okay, so writing our probability distribution for x, we have our random variable x, which is the number of tails in 3 tosses. What are the values that x can take on? Well, x could be 0, there could be no tails in 3 tosses, x could be 1, x could be 2, and x could be 3. So those are the possible values of x. And then we were given the hint to use the sample space to find these probabilities. So what is the sample space? That's all possible simple events. So that's, well, I could have 3 tails in a row, or I could have 2 tails and then a head, or I could have a tail, a head, and a tail, or I could have a head and then 2 tails, or I could have 2 heads, then a tail, or a head, a tail, and a head, or a tail followed by 2 heads, or lastly, I could have 3 heads in a row. So this is the sample space. That's the sample space for that experiment. That's the set of all possible simple events when I toss a coin 3 times. So let's use that to find the probability of each possible value of the random variable x. So in how many cases are there 0 tails? This is the only situation in which there are 0 tails. Each of those simple events is equally likely, so the probability that x is equal to 0 is 1 out of 8. The probability that x is equal to 1, the probability that there is exactly 1 tail, 1, 2, 3, there are 3 simple events in which there's exactly 1 tail, so 3 out of 8 is the probability of that event. The probability that we have 2 tails, 1, 2, 3. There are 3 situations in which we have 2 tails, so 3 out of 8 is the probability that x is equal to 2. And finally, there's just 1 situation where all 3 of them are tails out of the 8 simple events, and so the probability of that is 1 out of 8. So this is our probability distribution for that experiment, or for that random variable. So this random variable x, the number of tails in 3 tosses, is an example of a special kind of random variable called a binomial random variable, or a random variable with a binomial distribution. So in general, a binomial distribution has the following characteristics. It's a procedure in which there is a fixed number of trials. Usually n is the number of trials. So here we flipped a coin 3 times. So in our case, n is equal to 3. Our 3 coin flips are our 3 trials. Each of the trials are independent. So here, each coin flip is independent from one another because the outcome of one flip does not affect the probability of the next flip. So those trials are independent. The flips are independent. Each trial has 2 possible outcomes. They're usually referred to as success and failure. So for us, in this last example, our 2 possible outcomes for each trial are the coin could be tails or the coin could be heads. In this situation, we were looking for the number of tails in 3 tosses. And so therefore, success is a tail and failure is a head in this example. In general, that's just sort of the way that this has historically been talked about. So for example, if we were looking for the number of left-handed people in a group of 10 people, the thing we're looking for, that's the success. So being left-handed, or the individual being left-handed, would be a success. Being right-handed would be a failure. I'm right-handed, so I don't technically consider that, a failure on my part. But just in the language of binomial probabilities, the thing we're looking to observe is a success, and the other thing is the failure. The probability, and the last quality, is that the probability of success is the same in each trial. So in our example above, probability of success was 1/2, probability of a tail was 1/2 in each of the trials, and it remains the same. So those are the qualities of a binomial random variable. If a random variable fits all 4 of those criteria, it is a binomial random variable. We denote the probability of success as P and the probability of failure as Q. So in our last example, probability of head in one trial was 1/2. Probability of failure, probability of tails, this was probability of tails because that's what we were looking for, was 1/2. The probability of failure in our case, probability of a single coin flip being heads, was also 1/2. And in general, Q is always equal to 1 minus P because P plus Q is equal to 1. Each trial has 2 possible outcomes, success and failure. The sum of those probabilities must be equal to 1, so Q is equal to 1 minus P. The binomial random variable X is the number of successes in n trials. So X, the variable, is always the number of successes in n trials for a binomial random variable. So here's a few examples to think about. Are the following binomial random variables? If not, explain why not. If they are, what are n, p, and q? And also, what is success in that trial? So for each of the following, answer those questions. So first example, a die is rolled 80 times. Let X be the number of 4s that appear. Second example, 400 people are enrolled in a clinical trial. X is how they feel afterwards on a scale of 1 to 10. Third example, there are 30 red, 20 blue, and 15 green marbles in a jar. Marbles are selected one at a time without replacement. And we let X be the variable, the number of blue marbles chosen. And lastly, suppose that 20% of students who take the SAT score 600 or above in critical reading. Suppose 150 test takers are randomly selected, and X is the number of individuals with a score of 600 or above. So think about each of those examples and whether or not they are binomial random variables. Okay, for our first example, a die is rolled 80 times. X is the number of 4s that appear. All right, so here are the criteria for being a binomial distribution. Are there a fixed number of trials? Yes. N is equal to 80 trials, 80 die rolls. Are the trials independent? Yes. We know that die rolls are independent from one another. What you get on one die roll has no influence on what you get on the next one. Does each trial have 2 possible outcomes? So in the context of a binomial of this binomial question, our answer here is yes. And what are those outcomes? Our outcome is it's a 4 or not a 4. So it's either a 4 or it is not a 4. Those are the 2 possible outcomes. And success in a particular trial, in one roll, in one trial, is that the die is a 4. So that's what success is in this particular situation. And again, even though there's 6 possible values that the die could take on, X is the number of 4s that appear. So success is having a 4, failure is it not being a 4, and those are our 2 possible outcomes. Probability of success, the same in each trial. Yes, the probability of success in any one trial is 1/6, the probability that it is a 4, and the probability of failure in any one trial is 5 out of 6. That's probability, that's Q. The probability of failure, 1 minus P, is 5 out of 6. So yes, this is a binomial random variable. All right, next, 400 people are enrolled in a clinical trial. X is how they feel afterwards on a scale of 1 to 10. Are there a fixed number of trials? Yes, there are a fixed number of trials. Are they independent? We could say yes if these people aren't talking to one another or, anything like that. Does each trial have 2 possible outcomes? No, there's not like a yes-no situation here. So right now, the answer to this question is no, there are not 2 possible outcomes. And because we're asked how do they feel afterwards on a scale of 1 to 10. That's 10 different possible outcomes for each individual. If we were asked instead, like, X is number of people who improved in their symptoms or something like that, then that could be binomial in the sense that either they have improved or they have not. So we could change the way that this random variable is set up to make it binomial. So if we, said so this is no, this is not binomial. But if we said Y is number of participants whose symptoms improved or something like that, then that would be okay. That would be binomial. But we don't know the probability of success. We could assume that it is one probability, and that is what we're trying to find through the trial. So we can model that as a binomial distribution, but as this is currently stated, it is not binomial. All right, there are 30 red, 20 blue, and 15 green marbles in a jar. 10 marbles are selected one at a time without replacement, and X is the number of blue marbles chosen. So is this binomial? Well, it has a fixed number of trials. Yes, n equals 10. Are the trials independent? So this is without replacement. And so in this scenario, this is not independent because the marbles are not replaced after they have been taken out. So for example, if we say, okay, what's the probability that the first marble is red and the second marble is blue, for example, then it's 30 out of, how many marbles are there altogether? 50, 65 for the first marble being red, and then 20 out of 64 for the second marble being blue, whereas the probability of taking two marbles in a row is 30 for the first one, 30 out of 65 times, 20 out of 65 for the first blue marble, and then 19 out of 64 for the second blue marble. So the outcome of the first trial affected the probability of the second. So these trials are not independent, and so this is an issue, and then this is also an issue too. The probability of success in each trial is not the same. So this probability of success changes in each subsequent trial. Does each trial have two possible outcomes? Yes, and our two possible outcomes are blue or not blue. So there are two possible outcomes, but because these two criteria are not met, that means that this is not binomial. Again, we could fix this and make it binomial if instead of saying without replacement, we did this with replacement. In that case, this would be binomial. The probability of success in any one trial would be 15 out of 65. All right, last one. Suppose 20 students who take the SAT, 20% of students who take the SAT score 600 or above in critical reading. If 150 test takers are randomly selected, let X be the number of individuals with a score of 600 or above. So is this binomial? So first of all, is there a fixed number of trials? Yes. N, the number of trials, is 150. Are these trials independent? We would say yes, because these individuals are randomly selected. They don't have anything to do with one another. Does each trial have two possible outcomes? Yes. Either they have a score of 600 or above, or they do not. So success would be, in our case, a score greater than or equal to 600, and failure in a single trial would be a score less than 600. And finally, is the probability of success the same in each trial? Again, yes, these are randomly selected individuals, and the probability of success in any single trial, 20% of students who take the SAT score 600 or above, so P is 20% or 0.2. Q, the probability of failure, is 0.8. So what's really neat about binomial probabilities is that if we know what n, the number of trials is, p, the probability of success is, then we automatically know the probability distribution for any such binomial random variable. So if x is the number of successes in n trials with probability of success p in a single trial, then the probability of exactly k successes in n trials is given by n factorial divided by n minus k factorial times k factorial times the probability of success to the kth power times the probability of failure, 1 minus p, to the n minus kth power. This can also be written as n choose k times the probability of success to the kth power times 1 minus p, the probability of failure to the n minus kth power. So that's a mouthful, but let's break down what that formula means. So first of all, let's just see what that exclamation point means, that n factorial. So for example, 3 factorial is 3 times 2 times 1. And in general, for any positive integer n factorial is just n times n minus 1 times ... times each positive integer less than n. And we define 0 factorial to be equal to 1. So as an example, let's say that 10% of people are left-handed. What is the probability that exactly 2 out of 10 randomly selected people are left-handed? So this would be a binomial probability with looking for the probability that x is equal to 2. Our probability of success is 0.1, 10%, and our number of trials, n, is equal to 10. So here, the probability that there is exactly 2 left-handed people in this set of randomly selected individuals would be n, that's 10 factorial, over n minus k, 10 minus 2 factorial, times 2 factorial, and then multiplied by the probability of success. Probability of success is 10% or 0.1 times 2 the kth power to the 2, times the probability of failure, 1 minus 0.1 is 0.9, to the n minus k to the 10 minus 2. And so that's equal to 10 factorial, that's 10 times 9 times 8 times ... down to 1, divided by 10 minus 2 factorial, that's 8 factorial, 8 times 7 times ... down to 1, times 2 factorial, 2 times 1, times 0.1 to the second power times 0.9 to the 8th power. So we can cancel some of that factorial out. 8 times 7 times 6 times 1, blah, 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 is in both pieces. So those cancel out with each other. And we're left with 10 times 9 over 2, that's 45, times still 0.1 to the second power times 0.9 to the 8th power. And if we simplify that, if we multiply that out in a calculator, we'll get 0.1937 is the probability of having exactly 2 left-handed people out of a group of 10 randomly selected individuals if 10% of people are left-handed. All right, so where does this formula come from? Let's think about the example we just talked about, the probability of exactly 2 out of 10 randomly selected people being left-handed. To start, let's start with a slightly simpler problem. Find the probability that in this randomly selected group of 10 people, the first 2 people we interview are left-handed and the remaining 8 people are right-handed. So this is the probability of left and right and right in that order. First a left-handed person, then a left-handed person, then a right-handed person, etc. And so these are randomly selected individuals. This is independent, so we can use the multiplication rule. This is the probability the first person is left-handed times the probability the second person is left-handed times the probability the third person is right-handed times ... times the probability that the 10th person is right-handed. And so that's equal to probability the first person is left-handed is 0.1 times next one 0.1 times 0.9 is the probability that next person is right-handed, all the way down to 0.9 for the 10th person. And this is equal to 0.1 times itself twice, so squared, times 0.9 times itself 8 times, so to the 8th power. Okay, so that's part of the formula that we have above, but we're missing the factorial part. So how does this compare to the probability that we are looking for? So this is just one way for there to be 2 left-handed people out of 10 individuals, and this is like having it in that order. But we could also have had like a right-handed person and then a left-handed person and another right-handed person, left-handed person, blah blah blah, right-handed person. Those 2 left-handed people could come in any order. So we need to multiply what we have above by the number of ways to rearrange 2 left-handed people and 8 right-handed people. How many ways are there to rearrange those individuals? Well, if we have 10 people, there are 10 possible places, 10 possible people who could be first, and there are 9 people who could be the second person left because we've already got the first one. Who's our third person? There are 8 possibilities left for that, and there are 7 possibilities left for the 4th person, and so on. So 10 factorial is the number of ways to rearrange 10 people. But we don't actually care about the total number of ways to rearrange all 10 people. We only care about the number of ways to rearrange them only with respect to, are they right-handed or left-handed? That's all we care about. So we're actually going to divide by the number of ways to rearrange our 2 left-handed people, because we don't care, like if these 2 people switch, we don't care. And we're also going to divide by the number of ways to rearrange those 8 right-handed people, because if those 2 people switch, we don't care. All we care about is, are they right-handed or left-handed? And what order do they come in terms of being right or left-handed? So this is number of ways to rearrange the 2 left-handed people and the 8 right-handed people. We're dividing out by that number of ways to rearrange them because we don't care about the order of the individual left-handed people and the individual right-handed people. So that brings us to our formula, that the probability that x equals 2 is the number of ways to rearrange 10 people divided by 10 minus 2, the number of ways to rearrange 8 right-handed people, times 2 factorial, the number of ways to rearrange 2 left-handed people, multiplied by the probability of having 2 left-handed people in a row, multiplied by the probability of the next 8 people being right-handed, 0.9 to the 2. That is the formula that we calculated above. And again, this is number of ways to, or the probability of 2 left then 8 right-handed people multiplied by the number of ways to rearrange these individuals, only caring about the arrangement of right-handed and left-handed people respectively.